Welcome to the 2018 AWM AMS Noether Lecture. The Emmy Noether Lectures were established by the AWM in 1980 to honor women who've made fundamental and sustained contributions to the mathematical sciences. In 2013, in a bold but wise move, the AMS decided to co-sponsor the lectures with the AWM, and so the name is now the AWM AMS Noether Lecture. I'm delighted to introduce Jill Pipher as this year's Emmy Noether Lecturer. Jill has been and continues to be a beacon of inspiration for many of us. While she's a professor at Chicago, she encouraged our AWM past president, Kristen Lauder, to continue in mathematics, and now look where she is today. My friend Leslie Ward credits Jill with mentoring her and guiding her in every step of her career. Jill has many awards and accomplishments and accolades to her name, so I'll just mention a few. She was AWM president in 2011. That's when I came on the EC, and she has inspired me ever since. She was the founding director of ICERM, the Institute for Computational and Experimental Research in Mathematics. She's a fellow of the AMS and an inaugural fellow of the AWM. She's currently the Vice President of Research and Alicia Benjamin Andrews Professor of Mathematics at Brown University, and soon to be, very soon to be, President-elect of the American Mathematical Society. In addition to a ton of papers, books, and whatnot, Jill holds 4 patents related to the n-true encryption algorithm. So I know you're as eager as I am to hear Jill talk, so let's get on with it. I present to you with great pleasure, Jill Pipher.
Thank you very much for that really wonderful, warm introduction. And so let me start by saying that some topics, some areas in mathematics really lend themselves readily, almost effortlessly, to exposition to a general mathematical audience. For example, William Cook's lecture at 9 o'clock this morning. The topic I've chosen today may not be one of those, but I felt that I really should try to explain to a general audience why I have found these ideas so fascinating and compelling over several decades, and what the work of some of the discoveries that have been made over the years that I've been privileged to be a part of. So the plan for this talk is to describe, first I'm going to describe 3 theorems, 3 ideas, all from the same period, late 50s, early 60s, and indicate the scope of the mathematics that each one of these generated. Now I think in the case of one of them, it was fairly obvious right away that this was going to generate a lot of work. It solved an important problem right away. In the case of the other 2, I don't think it was so clear, the impact on mathematics that they would have. And so what also wasn't clear was really how many connections there were between these three ideas. So I'm going to explain how these connections evolved over the years, and then describe in the end some modern developments where really there's some very sharp and precise connections between these 3 ideas. So let me start with the first big idea. So the setting here is complex function theory, and Leonard Carlson is considering the following really classical problem in complex function theory. You're given a sequence of points, complex numbers zk in the disk, and an arbitrary sequence of complex numbers wk, and you ask what explicit conditions on zk are necessary and sufficient so that there exists an analytic function which interpolates that sequence, which takes on prescribed values at these points. It's a very classical problem, very natural problem, and so classical it was considered by Nevin Linna about 100 years ago and answered. But Carlson is seeking an explicit, checkable condition, and that's his interest. So he was led to formulate a dual problem, and and that entailed asking the following question. So suppose you have a measure, d mu, in the unit disk. So we're still in complex function theory. And g is an analytic function in the unit disk. And we're going to give it a sort of a norm, which you might as well, for the moment, if you're not familiar with this, think about this as the LP norm of this function on the boundary. You're measuring the size of this analytic function, the boundary values of this analytic function. So the question is, under what conditions on the measure do we have the following inequality? So I want to pause for a moment and look at some features of this inequality. On the left-hand side, you see an integral of an analytic function over the unit disk. So this is a solid integral. This is an integral in 2 dimensions. On the right-hand side, you see a quantity that involves g, the integral of g on the boundary. So this measure d mu has to have some kind of collapsing property. It collapses 2 dimensions to 1 dimension. So the condition on such a measure should involve this kind of collapsing property, and Carlson was able to answer this very precisely. So his answer was formulated in the following theorem. Mu is a non-negative measure on the disk. And mu is going to have the property that it assigns mass to a piece of this sector, which is precisely this collapsing of 1 dimension. So the sector that we're looking at has essentially carves out an arc on the disk of length L and goes into the sector a distance L. I'll have a better picture in a moment. But that's this collapsing property, and if a measure satisfies that, then this inequality is true. So he proved this for p equals 2 in the context of the Hilbert space L2 for harmonic functions. And an analytic function, real and imaginary parts are harmonic. So now he's taken analyticity out of the picture and reduced this to a question in potential theory, a question about harmonic functions. So if you have this, if you have this property for harmonic functions, you deduce this for analytic functions. And so now we can even ask this question not just in the complex plane, but in higher dimensions. And so we now can extrapolate this condition, this Carlson measure condition, to higher dimensions. So the condition on measures looks like this. If you're in, say, now we're in the upper half space instead of the ball, and we're looking at the boundary, which is just Rn minus Rn, and we have a cube or a ball. The geometry doesn't matter as long as the dilation is the same in each direction. We have a cube on the boundary, and we form this dome or tent or cube that lies above it. And we say that the mass that the measure gives to that dome or cube on top has to collapse to the n-dimensional Lebesgue measure of the base of the cube. So that's this geometric condition on a measure. And this question that Carlson asked was answered in 2 stages. First for point masses in 1958, and then later for general measures, where he came up with this condition. And his examples of measures that satisfied this property were, as you might expect, measures on lower dimensional sets, arc length measure on certain curves. So he's introduced this concept of a measure which is now honored with his name, a Carlson measure, to answer this question about analytic interpolation. So that's where matters stand. It's an interesting concept, but it was probably not clear how far this concept would go and how deeply embedded in many areas of analysis, geometric measure theory, and PDE this would become. So let's turn to the second theorem or big idea. So this emerged in a paper in 1961 by Fritz John and Louis Nierenberg, where they introduce a space of functions called the space of functions of bounded mean oscillation. So I realize that that not everyone in this audience thrills to the definition of a new function space, but I do want to try to convey the importance and interest of this new function space to even people that are not familiar with this range of function spaces that people in analysis and PDE deal with all the time. So these functions have a property that holds at all scales, and you'll see what I mean by that in a moment, which then induces this really remarkable self-improving property. So let me define the space of functions for you. So a function belongs to, bounded mean oscillation really captures the meaning of this, as you see. We take a function, we take a cube Q or a ball. Again, the geometry of the sets we're considering to measure the difference between this function and its average, its oscillation, if you were. The geometry of the sets we're considering are the ones that are invariant under a one-parameter family of dilations. They're the same in every direction. So we're not talking about measuring the oscillation of this function in long, thin sets. The geometry is cubes or balls. It doesn't really matter which in this context. So we look at the difference between the function and its average value, and we measure how big that is in this context of this L1 norm. Okay, so this is the space of functions of bounded mean oscillation. Now, if you're familiar with the scale of LP spaces, you might wonder where this sits on that scale. So let me say a few things about what functions belong to this space and where it sits in this range of things that might be more familiar to people in the audience. So what functions belong to BMO? Well, first of all, bounded functions belong to BMO, or more generally, functions that are bounded almost everywhere with respect to the measure, L infinity functions. Are there unbounded functions in BMO? And the answer is yes. On the real line, the log is a function that you can compute by hand, that it satisfies that bounded mean oscillation property for every interval on the real line. The John Nirenberg theorem in this 1961 paper says that this example is really quintessential, that the functions that are unbounded that belong to this space have logarithmic singularities. So here's the theorem, and I want to emphasize two aspects of it. So the theorem says you start with a function that has bounded mean oscillation, where that is measured in terms of this L1 size condition on F minus its average. And that has this remarkable self-improving property that you can actually say that it has bounded mean oscillation if you measure that difference using an exponential. And that exponential means that that exponential is sharp. That's the very best self-improving property you can say, which is why the log example is the example of an unbounded function here. So this function space has proven to be really significant in analysis and PDE. I mean, it had immediate interest, which I'll tell you a little bit about in a moment. But just for fun, I Googled bounded mean oscillation on Google Scholar and found a relatively huge number of hits. Also realized that John Nirenberg's original paper had been cited about 1,500 times, which is really pretty remarkable because many authors don't cite original sources in their papers. This represents a fraction, really, of the number of papers in which their theorem really appears. And then, just for fun, I thought I'd Google something else, some other household name, found Galois groups, but not quite as many hits, but I'm not trying to be competitive or anything. So what are some self-improving estimates and analysis that you're familiar with? Well, a differentiable function of a complex variable has derivatives of all orders. That's a self-improving property. A harmonic function satisfying a partial differential equation that requires two derivatives has derivatives of all orders. A function which is square integrable and also has its gradient square integrable actually has higher integrability, depending on the dimension. So these are all sort of self-improving properties that once you bring in a certain scale, a scaling property, you get this self-improvement. And these kinds of self-improving notions are really very powerful in analysis and PDE. So where do we find BMO functions? Well, Fritz John initially applied the John-Nirenberg theorem to the study of rotation and strain in the theory of elastic solids. BMO features very prominently in the theory of singular integrals. I wrote down an example of a singular integral for you, which you might find familiar from complex function theory. This is the Hilbert transform. It's defined as an integral operator with a kernel that has a singularity at x equals y. It's an example of many such singular integrals that feature in analysis in PDE, in the theory of summation of Fourier series, and in all kinds of contexts. This Hilbert transform is an isometry on L2, which is not easy to see from its present formulation. It's also a bounded operator on all these LP spaces. But the right space, when you go out towards the endpoints, the right space that emerges that Hilbert transform maps bounded functions into is BMO. In fact, this BMO condition is a really important testing condition. If you take a singular integral in some higher dimensions and you ask, is it a bounded operator on L2? Then the answer comes about by testing that this integral operator acts on one particular L infinity function by sending it to BMO. So that's a little bit of a lie, because I've swept a few important details under the rug, but it's really the heart of the matter. BMO emerges as the testing condition for boundedness of singular integral operators. So that's a very important, unexpected role that this space plays. In functional analysis, critical Sobolev spaces are, by critical I mean one derivative in Ln, in Rn, embed into BMO. And in complex analysis, the log of the Jacobian determinant of a quasi-conformal mapping belongs to BMO. BMO functions also arise in the study of well-posedness, of Navier-Stokes equations, for example, in this beautiful work of Koch and Totaro, and arise in geometric measure theory in the context of modern results that extend Lavrentiev's theorem on chord-arc domains, for an example. They arise in the theory of interpolation and as a dual space. So when you study LP spaces in real analysis, you find that they have certain duality properties. L2 is self-dual, it's a Hilbert space. An LP space is dual to another LQ space. And BMO also has a duality feature that brings it into this panorama of function spaces. And they also arise in the study of solutions to second-order divergence form equations. And this was really interesting. This was Moser's contribution to this theory, where he published in the very same issue of the journal in Communications in Pure and Applied Mathematics that published the John-Nirenberg result, an application of their theorem and their definition of this bounded mean oscillation function space. He had a new approach to some really important problems in PDE, and that's what I'm going to turn to next. So the third big idea is this, is this DeGiorgi, Nash, and now Moser study of the regularity of solutions to elliptic equations. This was initially driven by Hilbert's 19th problem, which is a regularity problem for a certain class of elliptic PDEs. A regularity problem means how much smoothness does the solution of this PDE inherit from the coefficients, given that the coefficients have a certain regularity. So affirmative answers to this were provided in these groundbreaking papers of DeGiorgi in the elliptic case, and by Nash in the parabolic case, for equations with a special structure, in second-order partial differential equations with a special structure, and the coefficients had no regularity whatsoever, no smoothness. They were not differentiable. They were not continuous. Moser gave another approach using this BMO theory, proving Harnack inequality. And so once a very small amount of regularity was established for these special equations, this could be sort of bootstrapped in certain contexts to higher regularity. So there was this really important, again, sort of self-improving property that took over once you proved that starting from really nothing but a structural condition on equation, you could generate a little bit of smoothness for your solutions. A concrete motivating example was the minimal surface equation. Okay, so let me tell you what the result was and what the context is. So we're looking at operators with a special structure. So these are divergence form. If the coefficients aij were differentiable functions, you could differentiate through and write this as a general second-order equation with the coefficients on the outside and some lower-order terms. But we're going to be in a situation where we're not going to be differentiating these coefficients. So this structure is going to play a very important role. In other words, this matrix of coefficients is just going to be very uniformly positive definite, but the coefficients are just bounded measurable functions. We're not assuming anything about the regularity of these coefficients. But that satisfies this uniform positive definite condition, which is ellipticity, which essentially says that all the eigenvalues of this matrix lie between two values and bounded away from 0. Now, the importance of the ellipticity condition in the context of this PDE is that the matrix A induces an inner product. It induces an inner product on the Hilbert space of functions whose derivatives are in L2. So notice on the right-hand side that expression is well defined if the derivative of u and the derivative of v belong to L2 by Cauchy-Schwarz. You can bound that thing because A is itself bounded. And if you plug in u equals v, you get an expression that from the ellipticity condition has this lower bound in terms of grad u squared. So this is the importance of this structural assumption. Let me give you, besides the Laplacian, which is an example of a lot of second-order PDE, let me give you a concrete example of an equation like this. So I'm in the upper half space, and in one quadrant I assign a certain matrix, which is skew symmetric, and in another quadrant I assign another matrix. K is a constant here. So in other words, I'm making my coefficients of my matrix, when I express it in divergence form, have a single jump at x equals 0. And so this matrix, so for example, A12 of this matrix is k when x is positive and minus k when x is negative, a single discontinuity. So solutions to this matrix are actually harmonic in each quadrant separately and satisfy a transmission condition across the line x equals 0. But you can write down explicit solutions. And you can see that in these cases of explicit solutions, as the constant grows, what's happening is that the Helder continuity is going to 0. So really, Helder continuity is the best you can say for these examples, and that is really the best that can be said. So why non-smooth coefficients? Well, you might take your favorite problem in a smooth domain, assigning a temperature distribution on the boundary and asking what the temperature is inside, but now you have an irregular domain. So you might want to make matters easier by mapping your irregular domain to a smoother domain. And when you do so, you find that mapping takes the Laplacian to one of these divergence form elliptic operators, but now the coefficients are not necessarily regular, and in fact may just be bounded measurable functions. Okay, so this celebrated DiGiorgi-Nash-Moser result says that solutions to such divergence form equations whose coefficients are merely bounded and measurable have to be Helder continuous of some order. And we saw in that example that our solutions did get some Helder continuity, but we don't know how much. But the Helder continuity depends on the ellipticity parameter. And that's really important because that's what allows one to bootstrap some of this small continuity into, in certain contexts, into more regularity. Okay, so it's like you get something for free, right? I mean, you're starting with an equation, the solutions have no regularity, the coefficients have no regularity, but the solution has a little bit. So it's a very powerful and possibly surprising result. But now, I mean, I know that you're sort of staring at this equation, divergence A of x gradient, and we can't really differentiate A of x. So what is the solution to this? What does it mean to take the divergence of A gradient of u, set it equal to 0? We're not differentiating through. So we have to give meaning to the notion of solution. And there's two ways you can think about it. I'm going to introduce the real definition of weak solution to this equation. But if you prefer, if this is really unfamiliar, you can think of what we're doing as saying that these solutions, these coefficients are all smooth, but we're looking for estimates that don't depend on any smoothness parameter. But here's really how you define a solution. When you say that L of u equals 0, what you mean is that L of u integrated against any test function phi is 0. So that left-hand side will always be 0 when L of u is equal to 0. Fine. And that's true for any function phi which is smooth and vanishes on the boundary. So now we get to integrate by parts. And we throw the divergence form over on the phi, we throw the divergence over on the phi, and we get an expression on the right-hand side that makes perfectly good sense, even though A of x is not differentiable. So that's what a weak solution is. A weak solution, now we're going to forget the left-hand side and just look at the right-hand side and say, if that's always 0, we've got a solution on our hands. Okay, so now I'm going to talk a little bit about connections between these because they started to emerge between these three things because they started to emerge already with Moser's paper in 1961 in this very same issue of this journal. So the connections are between BMO and between Carlson measures and between this theory of boundary value problems and for second-order divergence form equations. So the first connection was Moser's, which I mentioned, who gave an approach to proving this really remarkable result of DiGiorgi and Nash, who did this independently, by the way, by means of exploiting the self-improving properties of BMO. And there was, about a decade later, there was a really important and I think unexpected connection observed between BMO and Carlson measures by Charles Pfefferman, who used it to prove some duality results involving BMO, placing it on the scale and showing that it was related to a space, the Hardy space of functions, which had been around in complex function theory for already since the beginning of the last century. So here is Pfefferman's observation. Pfefferman's observation is so now we're back in the upper half space, let's say. We have a harmonic function which takes, so a harmonic function is determined by its boundary values, and so this harmonic function has boundary values which are, let's say, belong to the space bounded mean oscillation. Then that's a Carlson measure. So that expression may seem very specific and rigid, but let me just discuss a few features of it. First of all, the gradient squared is related to the equation. And the equation doesn't need to be the Laplacian. There are other equations, other solutions that could fit there. So there's a family now of Carlson measures. Now, the t there, what's the t doing there? Well, unless you do the calculation, you don't see why the t is there, but what the t really represents is the distance of a point xt to the boundary. So we could actually formulate this Carlson condition not just in the upper half space, but in other domains, replacing t by the distance to the boundary. So here's this huge family now of Carlson measures that's connected to potential theory, that's connected to harmonic function theory, and potentially to theory involving other equations. So now we have a family of Carlson measures that are not just arc length or measures restricted to lower dimensional sets. Okay, so this was, 1971, exactly a decade later. Okay, so now I want to talk about boundary value problems because that's the sort of area of more modern connections that I want to tell you a little bit about. And to do that, let me start by recalling some properties of harmonic functions. Now we're in higher dimensions. We're out of the complex plane where we know what a harmonic function is from the Cauchy-Riemann equations, but this has generalizations to higher dimensions. And a harmonic function satisfies this partial differential equation of second order, which is in divergence form. It's just the matrix is exceedingly simple. It happens to be the identity. So let's consider the statement, a harmonic function is uniquely determined by its boundary values. Not quite true, but it's almost true. I mean, for example, if you're in the upper half space, you can actually write down an explicit formula for a solution to Laplace's equation with prescribed boundary values, f. That explicit solution is possible because the domain has these symmetries that allow you to make this calculation. It's kind of a miracle. It doesn't happen too often. And in fact, on most of the domains in which you're considering solving these boundary value problems, you don't have an explicit solution that you can write down. But so the solvability of so this is called the Dirichlet problem. The Dirichlet boundary conditions are prescribing what the values that are taken on the boundary. So the solvability of this Dirichlet problem depends on the regularity of the boundary. In our case, this boundary is flat, but also somehow on the properties of the function of the data. And that's the sort of interesting area of boundary value problems is how the interplay between the geometry of the domain, the coefficients of the PDE, and the properties of the data all interact. Okay, so boundary value problems. We have our divergence form elliptic matrix, which we know we can generate solutions that have a little bit of continuity even when the coefficients have no regularity whatsoever, as long as it satisfies this ellipticity condition. Now, after some work and certain constraints in the geometry of the boundary of the domain, in general, if we want to solve this problem, find a solution, L of u equals 0, with certain prescribed boundary data, we can represent the solution in a way that's similar to this Poisson integral that I showed you in the upper half space, but we don't know exactly we don't have explicit formula for the representing measure. And so this representing measure that goes along with this equation L and goes along with this particular domain omega, this existence of this measure, which in the case of when L is the Laplacian, is just the harmonic measure on the boundary. The existence of such a measure is given to us by functional analysis, essentially by a Riesz representation theory. But we have this representing measure. We don't exactly know what it is, and we don't even know how it's related to other measures that live on the boundary that we understand better. Because we really want to compare this measure to measures that we understand. We have a boundary, let's say, that's regular enough to have a surface measure. Well, what can we say about the sets of measure 0 of these two measures? We're really mostly interested in conditions that say that these two measures on the boundary, the one induced by the operator when we're solving the Dirichlet problem, and the surface measure that we understand because it's somehow the restriction of Lebesgue measure to the boundary, we want to say that these two measures have the same sets of measure 0. We want to say this because we want to really be able to understand how to prescribe data on the boundary, which we can't do if we're going to be able to working with a measure that that perhaps has, is entirely singular with respect to surface measure. So we're interested in when these two measures are mutually absolutely continuous. And we call this condition A infinity. And it turns out that sharp and optimal answers to the questions about what is the relationship between these two measures, what's the connection with the geometry of the domain and the properties of the coefficients, they're really remarkably often answered in terms of Carlson measures. So let me tell you a little bit about some of these results and examples of how these more modern connections. I know that in some cases I'll be using some terminology from geometry like chord arc domains and rectifiable that you may or may not have heard, but I want you to just think about all these different ways of measuring the geometry of the domain and how precise you can make these connections to questions with and answers in terms of Carlson measures. So here's a particular problem. It's a perturbation problem. Suppose I have an operator with a matrix A1, a divergence form operator, and it satisfies some good properties, and its measure is really good, and I really understand all the properties about it. I can solve some Dirichlet problems. I understand what it means, what that measure looks like. And now I have another operator, which is some kind of perturbation of this. The coefficients, are a perturbation of the coefficients of this operator. How small, how large a perturbation can I take so that this next operator inherits some of the good properties of this old operator? And actually, the answer is a very precise one. And it was first noticed by Dahlberg that there was some connection to Carlson measures that answered this question. And a sharp answer was provided in this paper of Bob Pfefferman and Carlos Koenig and myself in, 1992. It's already 25 years ago. Okay. And so at least when the boundary of the domain is Lipschitz. And this has later been extended to boundaries of domains that are less regular, to chord arc domains, and even more general domains. So there's still a fair amount of work going on. The Kanto conjecture is another area where somehow BMO and Carlson measures came in a very surprising way. So Kanto posed this conjecture about perturbations of maximal accretive operators. And in the generality in which Kanto posed this conjecture, it was not quite true. McIntosh found a counterexample and reformulated it for a class of elliptic operators, which really was the intended application. The conjecture reduces to the solvability of a boundary value problem for a class of divergence form operators now with complex valued coefficients. So we're in the non-self adjoint case. Accretivity enables one to define a square root of the operator L. And the precise question is, what is the domain of this square root? When is the square root of L bounded in norm by the gradient the norm of the gradient of the function? And this, in terms of the semigroup that this has generated, this turns out to be a question about a boundary value problem for this operator L. And this question was out there for about 40 years before it was realized that really Carlson measures were that there was an important ingredient involving a Carlson measure estimate that needed to be proved. And that was resolved in the early 2000s by a number of people working together in various groups and building on a lot of previous work. So there were many steps toward this, but really the heart of the matter was finding a Carlson measure estimate. Another Carlson measure characterization of A infinity. So A infinity is this property where the measure induced by the operator, the representing measure, and the surface measure have the same sets of measure zero, are mutually absolutely continuous. So here's a test that we found for telling when that's true. And the test is expressed in terms of a Carlson measure estimate. If that BMO problem is solvable, if you can take your data in BMO and say that your solution always satisfies Charles Pfefferman's Carlson measure estimate, then you get this. Then you get this property about this. You can deduce this property relating these two measures. So this was a theorem of Martin Durst and Carlos Koenig and myself, building on some previous work, and we'll call this BMOsolvability. So the only catch here with this theorem is that it's not very checkable, in the sense that you start with arbitrary BMO data, and to get this bounded by the BMO norm, it's really a little challenging in practice. There are applications where we had some applications of this, and we were able to actually prove this. But what a slightly better theorem is proving this so a slightly better theorem is proving this not for all BMO functions, but for just the subclass of L-infinity functions that live inside of it. So there are extensions of this theorem to parabolic operators, applications of this to specific operators, and we can relax the boundary conditions on the domain. And now the final thing that I want to mention before I end is the connections to boundary. So the geometry of the boundary can be detected by BMO and Carlson measure estimates. And that's a really interesting and fairly recent development, spearheaded by some work of Hoffman, Martel, Mebaroda, and Garnett, Morgoglu, and Tolsa. So they prove that BMO solvability for the Laplace operator, in other words, you can always get this Carlson measure estimate for solutions for harmonic functions, actually says that the boundary has to be uniformly rectifiable. So now there's this interesting connection between this fundamental object of study in geometric measure theory, which is rectifiable sets, and this Carlson measure estimate. And the same statement can hold even for other operators. If we replace the Laplacian by a divergence form operator where the coefficients of the matrix A, satisfy a Carlson measure condition, then we can also make the same statement. Open problems in this field. So it may seem like we've gone very deeply into the study and detected quite a bit have a lot of detailed and very specific results, but the open fields, problems in this field are really, we're really just scratching the surface, because we're looking at second order operators, but there's a whole panorama of boundary conditions and operators that include systems of equations and higher order equations and free boundary problems that we really can't touch yet. So I just want to thank you for your attention, and I'll stop here. Thanks.
Thank you for the awesome talk. We're just going to have a photo op with the plaque, and then you all get to ask questions. Okay.
Probably just a few, since we have.
Yeah, just a few. There you go. Okay. Hold it. Where's our photographer? Come on, Jill. Where is he? A well-oiled machine, the AWM.
Well, I just get to stand here and hug you for a little bit longer.
Okay, thank you. Anyway, thanks, Jill. So we'll take questions now. There's a microphone there and a microphone over there. Any questions for Jill? I can't see.
Thank you for a beautiful talk, bringing out the connections between these three areas. Which part of these connections was most surprising to you?
I guess the connection between the BMO solvability and the A-infinity property of the measures, that you can make this quite so precise. I think we don't really have, that was the most surprising to me. Yeah, thank you. Thank you for that question.
Can you comment on what's happening for bounded domains?
What's happening for, well, so actually most of the theory takes place in bounded domains. I was really just, found it easier to illustrate some of these ideas by using upper half space or using unbound, but really most of the theory takes place in bounded domains, and there we don't have certain issues at infinity that arise in the unbounded case. And so it's actually much more well-developed theory in bounded domains.
One question here.
Just curious, did anybody study the best constant when you have BMO function, the self-improving exponential integrability? So you have a constant of the D, right?
Yeah, so
Anybody study that? Just curious.
so the sharp dependence on the BMO norm is understood, but best constants, no, I don't think. Maybe in the plane, yeah.
Okay, well, we better thank Jill again for her excellent talk.